How do you ensure selective coordination for electrical fault clearing? Imagine a power system where a fault occurs, but only the device closest to the problem trips, leaving the rest of the system running smoothly. That's what selective coordination aims to do. It's like having a smart alarm system that only sounds when it detects an intruder in one room, not the entire house. This approach is vital in power distribution and protection systems, especially in places like hospitals, data centers, or renewable energy sites where keeping power on is critical. To make this happen, engineers start with a detailed analysis of the system. They calculate the maximum fault current that could happen at each point. This helps them choose the right protective devices that can safely handle these fault levels. Devices like circuit breakers and fuses are selected based on their ratings for voltage, current, and how quickly they can trip. The goal is to match these devices to the system's needs carefully. Next, they look at the time-current characteristics of each device. These curves show how fast a device trips at different fault currents. Downstream devices should trip faster than upstream ones for faults within their zones. This means the curve of a circuit breaker on a branch should be to the left of the main breaker's curve. By doing this, only the device closest to the fault trips, isolating the problem without shutting down the entire system. Adjusting the trip settings is also key. Engineers set the pickup current, which is the level at which the device begins to trip, and add a slight delay if needed. This ensures that in case of a fault, the device closest to the problem acts first. They often use software tools or coordination studies to verify these settings before finalizing them. Once the devices are set, engineers document everything carefully. They run tests and simulations to confirm the coordination works as planned. If changes are needed, they revisit the device settings or even replace some components. It's also important to consider how these settings affect safety, especially in reducing arc flash hazards and protecting equipment. In real-world applications, such as in hospitals or renewable energy plants, this process ensures that power stays on for critical loads during faults. It's a balancing act, making sure protective devices trip fast enough to clear faults but not so fast that they cause unnecessary outages. By following these steps, electrical engineers can design systems that are both safe and reliable, keeping power flowing where it's needed most.